Hey y'all, this lesson is kind of part 2 to my first lesson on transformations of functions. In this video, we're going to be looking at reflections, stretches, and compression, or you might recognize that as stretching or shrinking. So we're going to be looking at the algebraic representation of that and how it looks on the graph and in a table. Also, at the very end of this lesson, we'll be looking at combining maybe not all of them, but most of the components of transformations into one function so you can see what things need to be done first. First, we're going to look at reflections, and to help us figure out what's happening with these reflections, we're going to do a table of values and then compare the graphs. So we have a square root function. We've got the parent function of a square root, and I've got some x values that I chose. I chose perfect squares because I figured it would just be easier to evaluate the function at those x values. We do square root 0, that's 0. Square root 1, that's 1. Square root 4, that's 2. And then we're going to graph this on the coordinate plane below. We have 0, 0, 1, 1, 4, 2. And we end up with this it's kind of like a half U shape thing. It's kind of like half of a x squared, not really, but they're inverse functions, so it's kind of is. And then we have the same function, but then there's a negative in front. So we're wanting to apply a negative to basically whatever we got here, which means that we're going to be taking those y values, and instead of these positive y values, where we're now making them negative. So we're going to be looking at a reflection kind of over the x-axis. So negative 0 is just 0, negative 1, negative 2. And this will look like 0, 0, 1, negative 1, 4, negative 2. And our little curve, well, I messed up at the end. Needs to keep going down that way. Our little curve is now flipped or reflected over. So these positive x values got reflected into the negative, not x, I'm sorry, positive y values got reflected into the negative y values, because we're literally taking what we got for y and making them negative. So how do these two functions compare? It is a reflection about the x-axis. So basically it's like when I say about the x-axis, that means it's a mirror image over the x-axis, which means that the y values changed. So for it to be moving from up here to down here, that's an indication that the y values are changing, even though we say reflection about the x-axis. In the next one, we have the negative inside the parent function. So we are going to, again, write these values for our parent function. We're going to graph it. We know what it looks like because we've already done it. And then you'll notice that I didn't use any negative x values. And the reason on this parent function, and the reason why I didn't do any negative x values, is if we plug that into the original function, when you try to take a square root of a negative value, it puts you in the imaginary numbers, which we haven't quite learned yet. So we can't use those to graph. That's kind of a side note. Not the point of the lesson. And then in the transformed function, I want to do negative x. So my x values are now going to be changing. And I had to use some different values here for my table, because if I tried to do negative x, I can't really take the square root. I can, but not for graphing purposes. And so I changed these so that I could get some values that I could actually take the square root of. And what's happening here is we have square root of 0 is just 0. And then square root of -1 is square root of 1, which is 1. And then square root of -4 is square root of 4, which is 2. So I have different x values, but my y values were the same. So now it's going to look like this. And if we compare the two functions, that function reflected, I can't do it, but I can't even do it with my hands, but that function reflected, there we go, over the y-axis because the x values were changing. So it is a reflection about the y-axis because the x values changed. For it to be flipped over that y-axis, that would indicate that it would be a horizontal change because those x values got flipped. And then if it's flipped over the x-axis, that would indicate that the vertical values are changing, which kind of goes along with the memory device that I used last time. And I didn't write that on these notes, but I do want to bring it back in because I think it still applies. We use the memory device HIVO, where horizontal change or movement happens when there's something that happens on the inside of the parent function, and vertical change happens when there's something on the outside of the parent function. So let's go back and see what I'm talking about there. Horizontal change, that's side to side, happens when the difference or the transformation is inside the parent function. So it got flipped horizontally, got flipped over the x-axis or over the y-axis. And then the vertical flip happened when the transformation was on the outside of the parent function. And just to summarize, when we have this negative on the outside, it's a reflection about the x-axis because it flips from up here to down there. And when the negative is on the inside, it flips about the y-axis. And if you're looking at the table, xy becomes x negative y on the first one. And if you're looking at the table for the next one, it's the x that changes for that horizontal movement. Now we have the case of stretching or compressing, or stretching or shrinking. And we're going to see two different scenarios here. In the first scenario, we have 1/2 x squared. So you might think, okay, I'm halving it, so it's going to be smaller. But let's just take a look at the table and then graph. Our original function, our parent function, is x squared. So if I square each x, I'm going to get 4, 1, 0, 1. It's a U-shaped graph. Went kind of fast there because we've already seen it. And I'm going to sketch this curve. And then in my transformed function, I'm taking half of each of my y values. So I'm taking half of what I got here. This becomes 2, half, 0, half. And then I'm going to plot my points. -2, 2, -1 goes to a half, 0, a half, and this will be symmetric. And when we draw that, whoops, and then compare the two functions, I was thinking my hypothesis was, or what you might have been thinking. I knew it was going to happen. Half, I was thinking maybe it's going to be smaller, but it actually ended up being wider. So the fraction in front of x squared yielded a wider parabola. That is the name for the graph of a U-shaped function. Now we will look at y equals 3x squared. So instead of a fraction, we have a whole number or a natural number. And because if it were 0, then that would make 0, and that's not quadratic. So a natural number. And based on the previous example with the 1/2 where it got wider, now I'm thinking with a natural number, it might shrink instead of stretch. So let's just take a look. We know the parent function, we've got 4, 1, 0, 1, and then now we're going to be multiplying each value by 3. So it's a 12, 3, 0, 3. And then the graph is on the next page. Oopsie. We know what this one looks like. 1, 1, 2, 4, negative 1, 1, negative 2, 4. I had to use a bigger coordinate plane to accommodate, and even 12 still isn't even on the graph, but that's okay. Let's see. So at negative 1, it went up to 3, 0, 3. And now we've got this skinnier parabola. So the 3 in front actually made it, I guess, stretch. I think I said stretch earlier for the wider one, but what's happening is it's kind of like stretching up this way. And you can kind of think of it as, how I like to think of it is, I kind of relate it to slope in my mind. So in the first one, we went up 1 over 2, and it made it wider. And then in this one, we went up 3 over 1, and that made it narrower. And so when we have a natural number, I'll leave it, natural number coefficient, it yielded a narrower parabola. So when our coefficient is in between 0 and 1, but not equal to 0 and 1, the graph widens. And then if the value is greater than 1, but not equal to 1, the graph narrows. It stretches, I believe. And if we put all of these transformations together into one problem, you want to first deal with a horizontal shift, then deal with stretching or shrinking, and then reflections, and then your vertical shifts are last. So with this problem here, I want you to try it on your own and then pause it and come back and check. There's several ways that you can view this problem. If you're stuck on how to move it, you can always use a table of values to help you at least get started and maybe get a better picture of it. So I did do a table of values over here, but I picked some different values, and basically I picked those values based on 0, 0. I knew that 0, 0 was going to have to go, that's my vertex in my first graph. I knew it was going to have to go right 2 and down 1. And this basically became my point of reference. And since I knew that this was my original vertex, and now my new vertex is moved right to down 1, then I made my table based on my new vertex, because I knew from this vertex, it's going to have to make a U from that. And then that's how I formed my table of values. So you can do it that way. Another way is I wrote over here, I have to go right to, I know it's going to narrow by a factor of 2, and I also know it's going to go down 1. So even still, I'm using the vertex as my point of reference when doing it with this method. So from 0, 0, I went right to down 1. That's my new vertex. And then from my new vertex, I need to kind of count out my my factor of 2. And if you'll notice, from 0, 0, if we kind of use the slope concept, we're going up 2 over 1 for that factor of 2. And since it's a U-shaped graph, we're going up 2 over 1, and that's how we know exactly how narrow it gets. And then we have our narrower shifted U-shaped graph. And our new vertex is 2, negative 1. So that is how it would look. I would be careful with moving anything more than the vertex. Your vertex is going to be that point of reference where you're basing your other points off of. But if you had tried to move, for example, 1, 1, left 2, down 1, you're not taking into consideration the factor of 2. So you have to be careful with that. Just to summarize that up, you do move your vertex, and then that's how you're going to form either your table of values or use that factor of 2 to find those second points that we're going to be graphing. And you'll notice that based on this, that's not necessarily something that you have to memorize as far as the order. If you remember from maybe algebra from high school or pre-algebra or whatever, PEMDAS, it's a popular memory device to help you with order of operations. And basically what this is doing is it's following the order of operations. We're dealing with parentheses first. The exponents make the U-shaped graph, and then multiplication, and then addition, subtraction. So our movement does follow PEMDAS, which is really cool. That is all I have for this lesson. I hope you enjoyed it. If you have any questions, please let me know, and I would be happy to help. See you next time.